Welcome to section 5.5.2, quadratic function transformation. So again, we're going to be focused on quadratic, but the patterns that we learned from the previous section, the patterns of rule for absolute value, is going to come up again in this section, and it's going to be very similar. It's just that quadratic will have a different form. So let's take a look at the parent function. So the parent function is f of x equals x squared. Now I give a second form over here, f of x equals open parenthesis, and then x, close parenthesis, and then the square on the outside. Now the reason I wrote out that form is to emphasize on the existence of parenthesis, and the reason is when it comes to parenthesis, it's going to help identify when it comes to reflections and dilation. But we're going to focus that on a later section. But again, this section is mainly with graphing and translation. But I want you to be aware that you can rewrite it with parentheses to help identify on specific transformations, such as reflection or dilation. Now, below it says rewrite function with vertex 0, 0. So here, you also see that we have parentheses, and inside the parentheses, it's x minus 0. That's for the x value. And then the plus 0, which is behind the parentheses, that's for the y value. Now, since this is the vertex, what we're going to do is we're going to put the vertex first on our xy table when it comes to graphing. Now, it's a bit different from absolute value, because absolute value, we start in the middle for the xy table. But here for quadratic, we're going to tie in to what we did in section 4.1 using the axis of symmetry. So for quadratic function, when it comes to graphing, we're going to put the vertex first. So let's start on the work for graphing. So again, as I stated, we put the vertex first, and then once you have written that down, what we're going to do is start identifying and graphing the right side. So we're going to be using the x value that's on the right of 0. So if 0 is in the middle, so my 2x value that comes at the right side is 1 and 2. So here's my 2x values that I'm going to use to make my coordinate points. Now, in this video, I'm just going to be focusing on the right side. You can do the left side if you like. It's just going to be the same process, just different numbers. Because eventually, if you do it correctly, you would and you should end up with the same graph as what we're going to have at the end of this example. So as I repeat, if we have this as a vertex, then simply use the next 2x value that comes after it. So if I start at 0, I'm going to use 1 and 2. And then what I'm going to do is I'm going to plug in these x values to make my y values to make my 2 coordinate points. So I'm going to show you the work, which is right here, and I'm going to explain it step by step. So for my first x value, x equals 1, I am simply plugging in 1 into x. So my first step is I have 1 squared. What I'm going to do is I'm going to expand, meaning I'm going to rewrite as 1 times 1. The reason I do this is, again, to be careful when you're working with negative numbers, so that if you're working with negative numbers, if you are doing the order of operation or PEMDAS correctly, then you should end up with the correct numbers, because you don't want to end up with a number with the wrong sign, and that would change up your y values, therefore changing up your coordinate points, and that could mess up your graph. So I would suggest on expanding, so that way you can multiply correctly. In the event you have negative numbers, you want to make sure you have the right number with the right sign. So at this point, I have 1 times 1, so I'm going to have parenthesis 1 close parenthesis. Now the reason I kept my parenthesis, in the event if you have something to distribute from the outside, you want to make sure you want to do that correctly. So in this example, since I do not have anything to distribute, I will let go of the parenthesis and then keep the number, which is 1. So that's going to be my y value for the second coordinate point. Now for x equals 2, I simply plug in 2 for the x, so I have 2 squared. So I'm going to expand, meaning I'm going to have 2 times 2. So once I multiply, I'm going to have 4, positive 4, and I still kept my parenthesis, and I keep it just in case if I have something from the outside in the front that I can distribute. In this case, I have nothing to distribute, no numbers, no negative sign. So then I'm just going to drop the parenthesis and then keep the number, which is 4. So this is going to be my y value for the third corner point. So once I fill up my y values and make my 3 coordinate points, I'm just going to plot on a graph, which is shown right here. So here's the vertex 0, 0. Here's my second point 1, 1. And then here's my third point 2, 4. So once you have plot your 3 points, simply start from the vertex 0, 0, and then just graph going through the second point and then going through the third point to make your right side of the graph. And as I stated before, if you start doing the left side, that's fine. It should be the same or similar or mirror image if it was done correctly. And if you did it correctly, then at the end we should have the same graph. So as I was saying before, start from the vertex, graph by going through the second and then the third point, and it should look like this. And then make sure you keep your arrows at the end of the graph. So once you plot the right side, what we're going to do from 4.1 is we're going to use the line of axis of symmetry. So the axis of symmetry is a vertical line that goes through the vertex. Now I'm going to plot the axis of symmetry, my vertical line that goes through the vertex like this. Now the great thing about quadratic graph is that in the middle is the vertex, and then when you draw your line of symmetry is that both sides are a mirror image of each other, so it's going to be an even graph. So, and you'll see what I mean by even graph and then the purpose of using the axis of symmetry. So now here we're going to start from the line of symmetry and then talk about how many units from the second point to the axis of symmetry. So looking from the axis of symmetry, if I were to count to my second point, it was basically 1 unit. So let me show you. From axis of symmetry to the second point, it was 1 unit to the right. So if I were to make my corresponding point on the left side, then I'm just going to go to the same amount, which is 1 unit to the left, and then plot my point here. And then I'm going to do the exact same thing to my third point. So starting at the horizontal of my third point, so from the axis of symmetry, meaning from the middle, if I were to count, I basically went 2 units to the right. Then I'm going to do the same amount, so 2 units to the left, to make my corresponding third point right here. Now once I have identified the 2 points on the left side, I'm simply going to graph from the vertex, go to the second point, and then go to the third point on the left side. Now again, it should be the same if you started on the left side and you're graphing the right side now. Here, we're going to finish up with the left side by graphing from the vertex, going to the second point, and then going to the third point. So your graph should look something like this. So this is the graph of the parent function. And again, the great thing about quadratic graph is that we just need to memorize these 3 points, either the right side or the left side. And once you finish graphing one side, you simply use the line of symmetry, the axis of symmetry, and then by counting how many units from the middle to the right side or to the left side, then you could identify the corresponding points on the other side of the graph. Now, what I do recommend is that you memorize these 3 coordinate points of the right side. Now, you could do the same thing for the left side if you chose to graph the left side first. It doesn't really matter to me which side you start off, right or left. But if you're going to do the right side, then these are the 3 coordinate points that you should memorize when it comes to graphing, because we will talk about how transformation affects these points, therefore affects the graph. So for the next example, we're going to focus on a new equation. So our new equation is g of x equals the square of x minus 3 and then minus 2. So now we actually have numbers that is involved in this equation. So first we're going to identify the vertex. So if we review with the rules that we had for absolute value, we're going to apply it to identifying the vertex when it's given in quadratic form or quadratic functions. So let's go over the rules for identifying the x and y coordinate of the vertex. So from absolute value function, we had opposite x and then same y. So when we apply it to this given equation, so for x minus 3, the minus 3 is with the x. So minus 3 is the same as negative 3. So the opposite of negative 3 is positive 3. So positive 3 is the x coordinate of the vertex. And then the number that's behind the parenthesis, that's going to be the y value. So the rule is same y. So since it's minus 2, which is the same as negative 2, then you're going to write negative 2 as the y coordinate of the vertex. So the coordinate of the vertex for this function, 3 comma negative 2. So this is the starting point that we're going to use when making our xy table. So just like before, the vertex is going to be the first point, and it's okay if you label this as the vertex. So that way you know where to start when it comes to graphing. Now, once you identify the vertex, then you just simply identify the next two x values on the right of 3. So if I was at 3, then my next x value is 4, and then after that will be 5. So you would identify and then write out the next two x values, which is shown here. So here's the next two x values. So once you identify the x value, what we're going to do is the same process in the previous graphing example, which is plug in these x values into the function to determine our y values so that we can make our second coordinate point and our third coordinate point. And I'm going to show you the work next. So the first x value that we're going to plug in is 4. So I simply plug in 4 into x. So that's why you're going to have 4 minus 3 inside the parenthesis, and everything else stays the same. So this minus 2 is going to be with us throughout the work. So following the order of operation, I'm going to simplify 4 minus 3, which is 1. And I still have the minus 2 in the back, and I still have the square. Now, 1 square, I'm going to expand into 1 times 1. When I multiply, it'll be 1 with the parenthesis. Let me repeat, it's going to be a positive 1 with the parenthesis, and then minus 2. Since I do not have anything to distribute from outside the parenthesis, I will let go of the parenthesis and then keep the number, but I still have the minus 2. So at this point, I can simplify 1 minus 2, which is negative 1. So that's the y value for the second coordinate point. Now I'm going to repeat the same process when x equals to 5. I'll plug in 5 into x, into the same equation. Now we have 5 minus 3 inside the parenthesis. And we still have the square, and then we still have the minus 2. That's going to stay consistent as long as you follow the order of operation. So 5 minus 3, that's going to be 2. So now we have 2 squared. So I'm going to expand and then have it written as 2 times 2. But don't forget, I still have that minus 2 in the back. So here, 2 times 2, when we multiply, that's going to be a positive 4. I still have my parentheses for best practice. And then carry down to minus 2. Now at this point, I'm going to examine. Since I have nothing to distribute from outside the parentheses, that's when I can let go of the parentheses and keep the number 4, and then bring down to minus 2. So at this point, I can simplify 4 minus 2, which is just 2. So that's going to be the y value of the third coordinate point. So once I identify my second and third coordinate point, I can start plotting on the graph like this. So here's my 3 points. Once I finish plotting the points, then simply we're just going to start from the vertex, graph to the second and third coordinate point to make our right side, which should look like this. Now, from there, we're just going to plot the axis of symmetry like what we did before. And again, it goes through the vertex right here. Now, from there, I'm going to look at my second corner point, and starting from the axis of symmetry at the horizontal of the second point, I'm going to count my units. So it was 1 unit to the right, therefore it's 1 unit to the left. So that's my second point on the left side. Then I'm going to do the exact same process for the third corner point. So at the horizontal of the third corner point, starting from the axis of symmetry, I'm going to count my units. So it's 1, 2 units to the right. I'm going to do the same amount, 2 units to the left. That's going to be my third corner point on the left side. So once I identify these 2 points, and you see how they're level, so each point are level with their corresponding points. From there, I'm just going to start from the vertex, go through the second point on the left side, and then go through the third point on the right side. When you do that, this is what the graph you should have. Next, we're going to talk about how this graph, how is it different from the parent function, and then identify the transformation. So here, on the left graph, we have the parent function, and then on the right graph, we have the second function, the square of x minus 3 and then minus 2, with the vertex at 3, negative 2, while for the parent function is the x squared with the vertex of 0, 0. So let's compare what was the changes from the parent function to the second function, g of x. So if I were to plot the vertex from the left graph to the right graph, so the vertex of the parent function is right here. So if we look closely, so the changes from the parent function to g of x was that it went from the vertex, from the initial vertex, it went 3 units to the right and then down 2 units. Now, even though I went right 3, you can still go the other way. So instead of going right 3 first, you could have gone down 2 units and then right 3 units next, and you still end up at the same spot. So this is the vertex of g of x. And again, you still end up with the same destination, same spot. It's just now let's take a look at the transformation. So basically it went right 3 units and then down 2 units. If I were to compare, say, another point, so say this point right here, let me circle that. So if I were to focus on that point, so at 2, 4, so 2, 4, which is right here, so this is the third point of the right side of the parent function. If I were to focus on the transformation, so if I start from the parent function to the new function, so this is the third point on the right side. So let's take a look at the transformation. Basically, you went right 3 and then down 2. Or you could have gone first, down 2, and then right 3. So essentially, it's the same transformation as what we did and examined between the two vertices. So let's talk about in terms of words. So if it's minus 3 inside the parenthesis, it's connected to when it's translated 3 units to the right. So let's say, and write out, translated right 3 units. Now you could also say or state move right 3 units. Now let's talk about the minus 2 that's behind the parenthesis. So the minus 2 is connected when the function g of x translated or moved down 2 units from the parent function. So if we would put in words, minus 2 behind the parenthesis means translated down 2 units. You could also state or write move down 2 units. So let's review. If it's minus 3 inside the parenthesis, it means that it translated right 3 units. And if it's minus 2 behind the parenthesis, it means that it translated down 2 units. So you can safely say that it's the same process, same pattern as what we did for absolute value. Then you could say that it would be the same pattern, same process if it's were the opposite signs or opposite operations in terms of absolute value translations. So we're in the third part. With this given equation, h of x equals the square of x plus 2 and then plus 1. So if I apply the rules for vertex, so the opposite x, so I look at the plus 2, which is the same as positive 2. So the opposite of positive 2 is negative 2. So negative 2 will be the x value of the vertex as shown here. And then same y applies to the number that's behind the parenthesis. So if it's positive 1, then the same y will be also positive 1 for the y value of the vertex. So we're going to be using this vertex to help us graph with the xy table. So let's take a look at the question here. What were the transformation from the parent function f of x equals x squared with vertex 0, 0 to the new function h of x equals the square of x plus 2 and then plus 1 with vertex negative 2, 1. So the first part is plus 2 inside the parenthesis. If we to compare the previous example, here it says minus 3 or negative 3 inside the parenthesis, then we describe the transformation as translated right 3 units. So for minus 3 or negative 3 inside, it translated right 3 units. If it was the opposite sign, then we can safely say that it went in the opposite direction. So for this one, if it's plus 2 inside the parenthesis with the x, then the opposite direction would be translated left 2 units. Now, you can also state it or write it as move left 2 units. All right, so for the next part, plus 1 behind the parenthesis. Again, if we compare it to the previous example, negative 2 or minus 2 behind the parenthesis, we describe the transformation as translated down 2 units or moved down 2 units. So again, negative 2 or minus 2, it basically means translate down 2 units if it's behind the parenthesis. So if we were to say the opposite sign, then we can safely say it will move into the opposite direction. So if it was plus 1 behind the parenthesis, then we can safely say that it translated up 1 unit. Now you can also state or say or write move up 1 unit. So again, if you compare these two transformations with their respective numbers and their positions to the previous example, you can see that in terms of opposite sign, they move in opposite direction. But to review, any number that's inside the parenthesis with the x is either left or right. In this example, since it's plus 2, it translated left 2 units. Any number that's behind the parenthesis is up or down. Now for this example, since it's plus 1, then the transformation is translated up 1 unit. Now we're going to talk about how these transformation affects the coordinate points, including this vertex, when we are graphing. Now, earlier, I mentioned that you should always memorize these three coordinate points of the parent function so that when you're graphing new equations or transform functions, it's always easy to know where you start. So this is going to be our reference point or our starting point when it comes to graphing, because these are the 3 points from the parent function. And what we're going to do is apply the transformation. So when you apply the transformation, then you're going to get new points, which I'm going to show you here. So let's take a look at the points, the coordinate points in the new table. These set of coordinate points should be corresponding to the equation h of x. Especially if you look at the first point, that's the vertex, -2, 1. So if I were to go back here, so here's the vertex, -2, 1, and then I go back to the xy table, it matches. Now, I'm going to talk about how the transformation affects these coordinate points and how it helps us determine new xy values for these coordinate points. So if I start at the vertex 0, 0, so let's talk about the x values. So if it's moving left or right, it pertains to the x. If it moves up or down, it pertains to the y. But like I said, we're going to focus on the x values first. So since it translated left 2 units, meaning move 2 units to the left, if I go to the graph, if I start at 0 and I'm moving 2 units to the left, so 1, 2, I stop at -2. So if I were to write this out algebraically, if I start at 0, which is from here, 0, and if I'm moving left 2 units, I'm basically subtracting 2. So 0 minus 2 is -2. Then I'm going to continue with the same process with the next x value, 1. So if I start at 1 and I move 2 units to the left, I'm going to subtract by 2. So 1 minus 2 is -1. Then my next x value, I'm going to start at 2. So right here, if I'm translating left 2 units, I'm going to subtract by 2. So 2 minus 2 is 0. Now, let's talk about the y values. So if I were to start at 0 for the y value, which is right here, and if I'm translating up 1 unit, I'm basically adding 1 to my starting point. So my starting point is 0. If I add 1, 0 plus 1 is 1. Then my next y value is 1. So since I'm translating up 1 unit, I'm going to add 1 to my starting point. So now we have 1 plus 1, which is 2. And then my next y value is 4. So if I start at 4 and I'm translating up 1 unit, I'm going to add 1. So we have 4 plus 1, which is now 5. So after I apply the transformation, then I have my new coordinate points for the new function h of x. So again, the first point is -2, 1, which is the vertex. Then the second point is -1, 2. And then my third point is 0, 5. After you identify the transformation, then you're going to plot the points and then start from the vertex by connecting the 2 other points, which is shown right here. So here's my vertex, -2, 1. Here's my second point, -1, 2. And then here's my third point, 0, 5. So once you start from the vertex and then connect to the 2 points, you have finished graphing the right side. Now, I'm going to apply the same process as what we did in the previous example, apply the axis of symmetry. So if I were to graph the vertical line through the vertex, here's my axis of symmetry, then I'm basically going to check how many units to see from the line of symmetry. So starting at the horizontal of the second point, and then from the axis of symmetry, I see that I went right 1 unit. So I'm going to go left 1 unit. And then I'm going to make my second point on the left side. Then at the horizontal of the third point, starting from the axis of symmetry, I see that I went right 2 units. So I'm going to go to the same amount in the opposite direction. So 2 units to the left. There I can mark my third point on the left side. Once I finish identifying all corresponding points, then I can start graphing from the vertex, going to the second, and then going to the third point. Once you graph that, then your graph should look like this. So this is another way where you can graph by applying the transformation without doing the work that I did before, which is plugging into the x value, using the order operation to determine the y values, and then just writing out the x, y, and the coordinate points. Here, we apply the transformation, which is seeing less work. As long as you apply it correctly, you will still end up with the same points in its corresponding spots. So again, if we were to compare the parent function, and it starts right here, 0, 0, this is a vertex. If we were to compare the transformation, it basically went from the parent function, the original, so 2 units to the left, and then 1 unit up. So if we were to check with the transformation that we typed out, translate left 2 units, and then translate up 1 unit, you see how it matches with what we identify here. So that means that we applied the transformation correctly and it got these coordinates correctly. Again, you can always check with the other coordinate points from the parent function and see how it lines up with all the other points. If you apply all transformation to each of these points, then they should line up correctly. So again, this is one way how you can graph by applying transformation.